Hello friends, I'm Dr. Kalpesh Amrutkar. Today we will see the prior and posterior distribution. Before going to start the prior and posterior distribution, we will firstly see the what is the exact approach of Bayesian inference. The Bayesian inference is just the process of updating our knowledge over a set of random variable given observed event. Means, suppose we want to inference about the binomial with parameter p and p is again on the what random variable. So that case, uh, if you know the p is random variable and having some distribution, so by using this knowledge, we estimate the uh, parameter by using this some basic knowledge or prior knowledge. So this one is the just Bayesian inference. Hmm. But sometimes some critique of Bayesian inference. So the main critique of Bayesian inference is that subjective priority. Well, subjective. There is no single method for choosing a prior, so different people will produce different priors and may therefore arrive at different posteriors and conclusions. These are the main critique of Bayesian inference. Also, there are philosophical objections to assigning probabilities to hypotheses, as hypotheses do not constitute outcomes of repeatable experiments in which one can measure long-term frequency. Rather, a hypothesis is either true or false, regardless of whether one knows which is the case. Like a coin is either fair or unfair. Treatment 1 is either better or worse than treatment 2. These are the some critics of Bayesian. But actually the advantage of Bayesian inference is that see, the probability of hypothesis is exactly what we need to make a decision. Using Bayes' theorem is logically rigorous. Once we have a prior, all our calculations have the certainty of deductive logic. By trying different priors, we can see how sensitive our results are to the choice of prior. This the main critic of Bayesian inference is कि different priors and then they take the different posterior. But using Bayesian inference, we try to see the which result are sensitive for that choosing the prior. It is easy to communicate a result frame in terms of probabilities of hypothesis. Even though the prior may be subjective, one can specify the assumptions used to arrive at it, which allows other people to challenge it or try other priors. The evidence derived from the data is independent of notions about data more extreme that depend on the exact experimental setup. Like this, you can see this part that this data more extreme. You can see the stopping rules. That case, you can see the how it working. Data can be used as it comes in. There is no requirement that every contingency be planned for ahead of time. These are the advantage or these are the answer of that critique of Bayesian inference. Okay, so before going to study the prior and posterior distribution, some basic terminology which is required for us or which is just uh, We called it like the probability of data given parameter is nothing but the likelihood, and the probability of parameter is a prior uh, function or prior distribution. Probability of parameter given data is nothing but the posterior distribution. So these are the part where this conditional distribution is nothing but, what is this conditional probability, which is equal to probability of parameter comma data, that means joint function divided by marginal, that is probability of data, and that probability of data is nothing but the summation of probability of data given parameter multiplied by probability of parameter, and the joint probability of parameter comma data, that is the parameter and data, this joint function is nothing but probability of data given parameter into probability of parameter, that means joint is equal to conditional multiplied by marginal, that we have to use here for this. So basically, what is the prior distribution? A prior probability distribution of an uncertain parameter theta is a probability distribution that expresses uncertainty about the parameter theta before the data are taken into account. That means, suppose x is a random variable having density function or mass function fx theta. A statistician may or may not have some prior knowledge or prior to random sample about parameter theta. This prior knowledge can be expressed through mathematical form called as prior distribution. This knowledge has to be properly represented and to be used to express prior knowledge or belief about parameter theta. Okay, like suppose x is a random sample, x1 x2 xn is a random sample from population specified by the probability mass function or probability density function fx theta, and it is required to estimate theta. Here we use the fx theta as whatever the x is a discrete or continuous, means f is a function which is mass function or density function, and let parameter theta is a random variable, it will have distribution. Okay, means what is, okay, as a result of the parameter theta being a random variable, it will have a distribution, and this allows the use of any knowledge available about possible values for theta before the collection of any data. This knowledge is quantified by expressing it as the prior distribution of theta. Then after collecting appropriate data, the posterior distribution of theta is determined, and this forms the basis of all inference concerning theta. And here we use the pi of theta as a prior density of theta or uh, prior function of theta. This is just pi of theta is nothing but the function of theta, which is a density function or mass function, whatever. Hmm? The information from the random sample is contained in the likelihood function for that sample, which is already told in previous slide. So the Bayesian approach combines the information obtained from the likelihood function with the information in the prior distribution. Both sources of information are combined to obtain a posterior estimated for the required population parameter. Okay, so here I have taken one example. Suppose x follows Bernoulli with parameter theta, where we know that in Bernoulli distribution, the range of theta is 0 to 1. I mean, theta is lies between 0 to 1. So here I have assumed that theta may be uniform 0 1, or theta is a beta first kind m and n, because in uniform 0 1 the random variable has taken values from 0 to 1, and again the in beta distribution with first kind having the range is 0 to 1. The range of values taken by the prior distribution should also reflect the possible parameter value. So you can take care of that. Whatever your parameter space, you can choose that corresponding distribution which is based on that parameter space. So if you want to prior distribution for a parameter that can only take values in the range, hmm, means suppose here this parameter theta has range 0 to 1 and you have to taken the gamma distribution. So this is just a silly for considering the prior. So here the just graph of the suppose theta is from the uniform 0 1, so this is the square function, and in the beta first kind it's like that the curve is look like. This is just the idea about the prior distribution. Okay, so then after we will see the posterior. So posterior density of theta given A is determined by applying the basic definition of conditional density. Okay, that means your theta given x is nothing but the joint function of x and theta divided by f of x, and this joint is nothing but the conditional multiplied by marginal. That means fx given theta into pi of theta divided by f of x. This is just the prior function, this is likelihood function, and this is your whole function that nothing but the integration over parameter theta into f of x given theta into pi of theta d theta. So here if your theta takes values from that corresponding interval, or the theta is a continuous random variable, then you take the integration. If the theta is a discrete random variable, so that case you can use here summation uh, in the replace the summation by that integration. You can here use just summation over fx, summation over theta fx given theta pi of theta. This is just the used by the discrete case, but most of the case is the theta is the random variable which is just continuous random variable. Even your x is a discrete. For example, if I have to taken the x is the binomial random variable having parameter n and p, so p is like between 0 to 1. So again p is a continuous random variable, so that case you can use the integration that case. Or I have to assume that kx follows Poisson lambda, and lambda is lies between 0 to infinity, so you can here use the gamma distribution or exponential. So it is again the continuous, but sometimes the theta is the discrete random, so you can use the summation sign. So okay, so in that posterior distribution you can see that the posterior is the proportional to the prior times the likelihood. This posterior is directly proportional to the prior times likelihood. Okay, this is just the idea about the posterior distribution. For example, I have to take one example. X follows binomial with parameter n theta. So mass function of this random variable is fx theta is equal to ncx theta is to x 1 minus theta is to n minus x, where x is lies between 0 1 to up to n, and theta is lies between 0 to 1. And we know that this theta is a random variable and having density function beta first kind with parameter a and b. So that case pi of theta is equal to 1 upon beta a b theta is to a minus 1 1 minus theta is to b minus 1, where theta is lies between 0 to 1 and a and b are positive. So posterior distribution is theta given x is equal to conditional fx theta into pi theta divided by integration over theta fx given theta pi of theta into d theta, and we know that this fx theta is ncx theta is to x 1 minus theta is to n minus x multiplied by 1 upon beta a b theta is to a minus 1 1 minus theta is to b minus 1 divided by integration over theta ncx theta is to x 1 minus theta is to n minus x divide multiply by 1 upon beta ab theta is to a minus 1 1 minus theta is to b minus 1. Okay, so here ncx is independent of theta and 1 upon beta ab is again independent of theta, so which is outside the integration sign and cancel with that numerator ncx into 1 upon beta ab. So these both terms are cancelled, so only remaining terms are theta is to x into theta is to a minus 1, that means theta is to x plus a minus 1, and 1 minus theta is to n minus x into 1 minus theta is to b minus 1, that nothing but n minus x plus b minus 1, and divided by integration over theta. Theta is nothing but 0 to 1, so integration over 0 to 1, and this numerator term is as it is theta is to x plus a minus 1 1 minus theta is to n plus x minus n plus b minus x minus 1 d theta, and this integration is nothing but the beta function with parameter x plus a n plus b minus x. So this beta function nothing but 1 upon beta x plus a n plus b minus x theta is to x plus a minus 1 1 minus theta is to n plus b minus x minus 1. So this is, and here theta is lies between 0 to 1, x plus a is your positive, x is a discrete random variable and it takes the value 0 1, that means it is again positive, so x plus a is also positive, n plus b minus x, so n is the number of trials, so that means which is natural number, and n is greater than your x or equal to x, so n minus x is positive and b is also positive, so n plus b minus x is also positive, so that means this is the beta distribution. This is the density function of beta distribution with parameter x plus a n plus b minus x. So that means this posterior distribution is beta first kind x plus a n plus b minus x. Okay, so thank you so much.